to do for this assessment is question number 1. It has I think it starts from part A to part H. The first one will start by reading the question. An electron with a charge of negative equals to 1.60 times 10 to the negative to the negative 19 power coulombs is at the rest at a distance of 1.00 times 10 to the power of negative 10 meters from the center of a lead nucleus. Charge of that's the charge. You may treat both objects as point charges. How much work would you have to do to move the electron to a distance of 5.00 times 10 to the power of negative 10 meters from the center of the lead nucleus? So first I'm gonna start with drawing a diagram. So I'll draw a lead nucleus and I label it positive 1.31 times 10 to the power of negative 17 coulombs, and then I'm gonna draw the electron and then label it negative 1.60 times 10 to the power of negative 19 coulombs. So let me draw the diagram. So black. So we're going to start by making the first distance, which is this one. I can't really draw, but it's this one. So we're gonna do that. I'm gonna label it here I1. I refers to the distance, or sometimes radius, but in this case we're gonna do distance. So the distance is 1.00 times 10 to the power of negative 10. So that's, and then we're gonna do the second distance, which is how much work would you have to do to move the electron to a distance of 5.00 from the center of the lead nucleus. So so this is how much. I'm just going to do my best to draw it. Meters. So 5.00 times 10 to the power of negative 10 meters. So let's draw it here. Just use a random color. So this is gonna be the lead. So I believe it's PB, and so we're trying to, and then this is gonna be the negative electron right here. It says I believe it says right here. Okay, an electron charge negative E equals to negative 1.60 times 10 to the power of negative 19. C is at a rest at a distance from the center of the nucleus. So basically it's at the center, and then we're gonna also, so the thing is we're trying to see how much is the work, how much the work is, like how much is the work would be to move the electron from the center to the lead nucleus. So how much it would be if we would push it here. So like how much would that be? So W equals work equals like how much. So to for the starting distance between it is the R initial, which is this one right here, up here. We're gonna name it R1, or R initial is the same thing, and then we have the R final, which is gonna be R2. So this is basically the new distance, R final, which is gonna be 5.00 times 10 to the power of negative 10 m. So we're just trying to see how much is like between this here. But since the electron has like a negative charge and the nucleus has like a positive charge, they attract each other because I'm moving the electron farther away. I have to do positive work against the electric force, basically. So now I'm going to solve the problem. So the work done by the external force equals the change in the electropotential energy. Excuse me. So I'm gonna write the equation. I'm gonna write it here. So we're gonna do work is gonna be equals to delta U equals to U final. We're gonna put F for final, and then we're gonna do minus U initial, which is gonna be the I. And then the equation for the electric potential energy is gonna be the equation that we use normally in the textbooks. So it's U equals to 1 over 1 over oh wait, no, sorry, I made a mistake. I meant to put the potential energy equation. So that's U equals to K times Q1 times Q2 and divide that by R, which is the distance. And so Q represents the electric charge and R represents the distance between the two charges, and K is the Coulomb's constant. So substituting the potential energy equation into the work equation basically gives the work is equal to K times K times Q1 times Q2 times the quantity 1 over 1 over R final minus 1 over R initials. And so now I'm going to substitute the known values. So we know that K is equals to 8.99 times 10 to the power sorry, 9 neutron neutron, I think meter squared, and I believe it's -2. Hold on, let me check real quick. Yes, it's right. Just right. So it's K is equal to 8.99 times 10 to the power of negative to the 9 neutrons meter squared per Coulomb squared, and then Q1 is equals to negative 1.60 right here. Yeah, negative 1.60 times 10 negative 19 coulombs, and then like Q2, which is gonna be 1.31 times 10 to the power of negative 17 coulombs, and RI is going to be 1 point times whatever we had at the top here. Negative 10 meters and final 5.04 times 10. So you're probably wondering, where do we get the Q1 and Q2 from in the problem? So this is because Q1 is the charge of the electron, which is the negative 1.60 up here, and then the Q2 is the charge of the lead nucleus, which is going to be the positive right here, 1.31 times 10 to the 17 right here. And then we already knew they also gave us in the equation. So these are all our givens basically that we had. Okay, now I'm gonna do, after substituting these values, and yeah, after substituting these, we're gonna basically plug them in. So let's plug these values in. So we got W equals to 8.9. This is the K here, so we're gonna start with K. K right here. Let me different this one. Okay. 8.9 times 2. Close parentheses. Now we're gonna do Q1, which is up here. This is negative, so make sure you add your negative sign. 1.60 times 19 columns, and then we're gonna do Q2, which is 1.31 times 10 negative 17. Let me make it smaller so everything fits. Okay. And now what we're gonna do is we're gonna do this one right here. So we multiply. I'm gonna do 1 over RF. RF is like this one, which is 5.0 times 10 negative 10 meters. Minus that by 1 over 1.00 times 10 negative 10. Close the parentheses. Okay, now we're gonna solve it. I know I'm gonna use the calculator, but I'm gonna do each step while using the calculator. So just so we're gonna do 8.99 times 10 9 multiply by 1 negative negative 1.60 times 19 multiply by 131 times 10 negative 17 columns, and this is gonna give us all negative 1.884 times 10 negative 26. Hold on, double check. Joules, I believe that's how you pronounce it. Yeah, joules. It's gonna be joules. Joules meters. And then we're gonna calculate the section here. Let me put, okay, let me plug it in. 1 negative 10 negative, okay, so 1 over 1.00 times 10 over 10, negative 10. Close parentheses. So in my calculator, I got so I got so let's do it separately. So I did the first part here, 1 over 5.00 times 10 to the power negative 10, and I got in my calculator I got 2.00 times 10 to the power of 9, negative 9 actually. I believe that's yeah. So now I'm gonna do the other one, which is 1.0. Okay, so for this one I got subtract by 10.00 times 10 over 9 equals that to negative 8.00 times that by 10, 9. And sorry, I meant to say meters. I think it's gonna be meters. Per meter actually. Yeah, that's what I got. And sorry, my mistake here. Let me try that. Okay, and then W work is equals to, now we're gonna do everything together. So we have to multiply everything together since we did this part separately. And we did this part separately. And now we're going to multiply both of these together. Negative 1.884 times 10 to the power 26 joules times meters. To multiply that by negative 8.00 times 9 per meter, and let me plug that into my calculator. So we're gonna put negative 1.884 times 10 negative 26, and we're gonna multiply by negative 8.0 10 to the power 9 per meter, and I got my answer as, I'm gonna round it, so I'm gonna get 1.50.7. So if you round it, that's just and then times 10 to the power of I guess 16 joules. But if you're gonna round it at the workbook, it's gonna be 1.5 times 10 negative 16 joules, and that's how I got my answer for number 1. I hope I explained it pretty well in depth. Now I'm gonna just add a few pages. Okay. Now let's do part B. Part B. I hope I labeled the first one. Hold on. Oh, I didn't. Part A. And then this is part B. So then part B is basically connected to part A. So let me read it. If you release the electron from the position in A, what will be its kinetic energy when it is a distance 8.00 times 10 to the power negative 12 meters from the center of the lead nucleus. You can assume that the lead nucleus remains at rest since it is more massive than the electron. So for this one, I'll redraw the diagram similar to the first one. So um, okay, let me rewrite everything. R1 in the beginning was this, and R2 distance. The final distance was, so that's the same from, okay, from the, we're copying basically whatever we wrote, we drew in the diagram of part A. Okay, so my diagram not too perfect basically, but try to make it longer. Okay, so here is the lead, which is the plus 82E. And then in the middle we had in the center, which is the negative electron, and then the negative electron to the end is basically trying to see so it's asking what will be its kinetic energy when it's the distance 8.00 times 10 to the power of negative 12 meters from the center. So basically this is attractive force. So the give me a minute to think. I made a mistake, I believe. I think the R1 should be 5, I believe, and the R2 should be 8, since here it says what would be the kinetic energy when it's the distance. So I'm believing that's what it says. And since I drew the electron closer to the nucleus and labeled the final distance of the R final, which is R2, to 8.00 times 10 to the power of negative 12 actually. I made another mistake. Okay, so since the electron is negatively charged and the nucleus is positively charged, they attract each other. So basically the electron moves closer to the nucleus, and its electric potential energy is decreasing, and that basically lost the potential energy to convert into kinetic energy. So I'm going to use the principle of conservation energy. In the equation for this one, it's going to be initial so it's gonna be the K1, or initial kinetic energy plus the potential energy, which is U, and then the final is gonna equals to the final plus the final potential. So since the electron basically starting from the rest, the initial kinetic energy is 0. Rearranging the equation gives the final kinetic energy that's going to equal to the initial potential energy. So let me write that down. So the final kinetic energy is going to equal to the initial of the potential energy minus the final of the potential energy, which is U2. And so the equation for the electric potential energy is going to be U equals to K, which is the constant, K times Q1 times Q2 divided that by R, which is the distance. So the Q, remember, represents the electric charge. So substituting the potential energy equation into the conservation of the energy equation is going to give us this is going to be kinetic. It's a final kinetic. So it's going to give it be Q2. I'm assuming Q2 equals to K times Q1 times Q2 times the quantity over R1. I think I'm writing it wrong. Let me double check the formula again. I think I made a mistake. I think that doesn't come yet, but so we're gonna do so we're gonna solve it. So let's first start by multiplying Q1 times Q2, and in the last equation it already told us it was in part A right here I'm showing right here negative E is equal to negative 1.60 times 10 to the power of negative 19. So that was Q1. So let me write that down. Columns. And then multiply that by 1.31 times 10 to the power of 17 column, which is also given here. Right here it says the charge is plus 82E, which is the lead. And this is and in my calculator that gives me negative 2.096 times 10 to the power of negative 36 coulombs squared, because it's so now we're gonna start with individually doing the potential energy. I'm doing a different method. I believe there's two methods for this equation, I'm assuming. But I'm doing the methods. So we're going to find the potential energy. So that's what the U stands for. The U is basically the electric potential energy. So we're gonna divide by the initial ones. So that's gonna just 8.99. This is just starting. So the K is equals to K is the constant of the Coulomb's law, I believe, and it's 8.99 times 10 to the power of 9. Multiplying that by what we got up here, which is Q1 times Q2, which is multiplying it. Let me just erase that, it was confusing. 0.096 times 10 to 36 coulombs and over 1.00 times 10 to that's the R1, basically the initial distance, and then we can also write down the second potential energy. This is the final potential energy basically. So it's basically the same thing what we wrote for Q for U for potential, and the bottom it's going to be a little different because the R2 for this one is 8.00 times 10 to the power of negative 12. So I'm going to put it in my calculator and solve them. Okay, so I got negative 1.884 times 10 to the power of 16 joules basically. Yes, that's what I got. Negative 1.884 times 10 to the 16 joules. And for the second one, I got negative 2.355 times 10 to the power of negative 15 joules. Okay, so once we got that, we're gonna do the final, which is finding the kinetic energy, the final kinetic energy, which is K2, and that's gonna be U1 minus U2, the potential, the initial potential minus the final potential, which we wrote up here. So to do that, we're going to basically get this answer and this answer, and we're going to subtract it. So negative 1.884 times 10 to the power negative 16 joules minus negative 2.355 10 to the power. So let me put that in my calculator. 1.884 times 10 to the power of negative 16 joules minus negative 2.355 times 10 to the power of negative 15 joules. And my answer is I'm gonna round it. So I got 2.16666. So I'm gonna put it as rounding it, we're giving 2.17 times 10. Okay, it says E negative 15, so 10 to the power of negative 15 joules. So to round that is gonna be 2.2 times 10 plus negative 15 joules, and that's what the that's what the let me add equals to K2. So that's what the kinetic energy is gonna be when the distance is 8.00. So when the distance right here is this is how much it's gonna be the kinetic energy. Well, because we did basically what we did was we got the initial potential energy and subtracted by the final, and that's the answer we got. Okay, now I'm gonna do is part C. So that's also in the same wait, I think this is a separate question. Yeah, this is a separate question. So let's go here. So let me read it. It says in a nuclear physics experiment, a proton mass 1.67 times 10 to the power of negative 27 kilograms, and a charge of positive a positive charge it it is equal to positive 1.60 times 10 to the power of negative 19 coulombs is fired directly at the target nucleus of unknown charge. You can treat both objects as point charging and assume that the nucleus remains at rest. And when it is fired from its target, the proton has speed 2.50 times 10 to the power of 6 10 to the power of 6 meters per second. The proton comes momentarily to rest at a distance 5.29 times 10 to the power of negative 13 meters from the center of the target nucleus, then fires back in the direction where it came from. What is the electric potential energy of the proton in the nucleus when they are 5.29 times 10 to the power of negative 13 meters apart? So I'm going to start by drawing a diagram. So I'm going to draw a target nucleus and then label it as like the charge as Q, since it's going to be unknown. And then I'm going to draw the proton approaching the nucleus and label it positive 1.60 times 10 to the power of negative 19 coulombs. So let me draw like a diagram of that. So we're gonna draw a proton here. Proton. First, let me write the part C. Draw proton. So the proton mass is, we're gonna write it as proton. So it's a proton and positive, so we're proton, and we're gonna write here 1.60 and 10 negative 19. See, that's what I want to write. I think I made a mistake. This is not what I meant to write. So we have actually two. So we have two protons. I think, yeah, we're gonna draw two circles. So proton 1, and then we have the blue for this one. another proton. So this one's a little far from the nucleus, and the proton has the initial speed of 2.50 times 10 to the 6th meter per second. So let me write that here. Oops. 2.50. Okay. This one, I'm going to write near the target. So near the target. This is gonna be the target. And we're gonna name it as Q because it's unknown and we don't know. Mm, so we know that the so basically far away from the nucleus, the proton has an initial speed of 2.50 times 10. So like right here. So at the closest distance, 5.29 times 10 to the negative 13 meters, the proton momentarily comes to us before moving away. So basically, it's gonna bounce back basically. So the this is the distance. The 5.29 times negative 13. Okay. So it's from the center of the target nucleus and it flies back to your direction from where it came from. So that's D. So we do direction. So let me also write the mass here, which is 1.67 times 10 kilograms. And we're going to do is the speed. For speed, I'm going to use hold on. V for the speed, and the speed is 2.50 times 10 6 seconds. So the equation for this I'm gonna use is, so first I'm using conservation of energy. So the equation for this one is going to be initial kinetic energy plus initial potential energy equals to final kinetic energy plus final potential energy. So let me write that down. So it's going to be K I initial du potential equals to final plus potential final. So when the proton is very far away, the electric potential is approximately 0. So at the closest point, the proton speed is going to be 0. So the final kinetic energy is also going to be 0. So this is going to leave us to the initial kinetic energy equal to the final kinetic energy. I believe that's how it's going to be. So let me, so the kinetic energy equation is going to be K equals to 1/2 mv squared. So it's mass and then speed squared to half. So now I'm going to substitute the known values. So the mass is, as we know, I wrote it down. So we're going to plug everything together and do 2.50 times 10. Give me just a second. Times time we're gonna do meters. I didn't outline. So we're gonna square this because it's v squared. So first, I'm gonna square this. Actually, let me get a charge.